Okay guys, today's video is going to be about antenna theory and about the differences between regular two-way antennas and microwave dishes. To start off with, I'm going to talk a little bit about what we're trying to get an antenna to do, so we know exactly how they're supposed to work. And basically what we have, and I'm going to start by using a typical VHF, it's a Motorola repeater as an example, to show the process of how we're going to take power, in this case from the power company, and we're going to transform it into a portion of that power that we take. We're going to transform a portion of it into electromagnetic radiation, and the process that we do to do that. It's important to understand when you're starting off with antenna theory is to the one concept that you have to master, and that kind of rules the day in the whole subject, is the law of maximum power transfer. And basically, to sum it up for in the radio business, what it's saying is if you want the maximum amount of electricity that you feed to an antenna to be transformed into electromagnetic radiation, well, the impedance, the load of the antenna needs to match the impedance of the radio. And in this particular case, we're dealing with 50 watts, or I should say 50 ohms, and that's the standard impedance that we use in the radio business, and that's not really adjustable. So it makes it to where we have to run our equipment in a very inefficient manner, which means we waste a lot of power on heat to get the product that we need. But for our purposes, that's okay, and that's not a big deal. If you start out with the repeater itself, the PG&E gives us the power. In this particular case, when we're transmitting at high power, we're going to be drawing 534 watts, and from that 534 watts, the power supply is going to take 280 of it, and we lose 250 watts in running the power supply. Once the power supply provides power to the radio takes 280 watts in, but only gives 100 watts out to the antenna, so we lose 180 watts through the radio. And in perfect conditions, we're going to lose 100 watts across the heat sink to match the 100 watts that we have going out to the antenna, because we want that maximum power transfer. We want to get the full 100 watts out. So to sum it all up, what we're doing is we're starting off with electricity that's coming in at 120 volts AC and 60 hertz, and we're transforming that electricity into a different frequency, in this case 150 megahertz, and the volts are are going to be 70 volts, and now that signal is going to be frequency modulated with intelligence, with information that we put on through a microphone or other input. And now that electricity is going to go up to the antenna, where it is going to be transformed into electromagnetic radiation. Now, antenna theory is not very intuitive, and it can be difficult to understand, because there kind of is like some magic involved, in that there's a thing called resonance, and that's what dominates everything with antennas. And The best analogy that I can come up with is an antenna is very much like a balloon made of steel. And on this balloon that you have, no matter how you try and push into it, or another good example would be a bicycle tube. I would say a bicycle tube that's made of steel. And you have an air pump hooked up to it, and no matter how hard you push or pull, you can't get any air to go through this particular bicycle tube. However, it has this magical ability that if you get the rhythm just right of the frequency that you're trying to pump air into it, all of a sudden this steel tube will transform into rubber, or it's pliable so that you have the ability to now pump air into it. And what an antenna does is it does similar to the same thing when you're trying to put voltage on the antenna rod here. As you apply voltage, there is an insulator between the center conductor, here it's easier to see here, but the insulator between the center conductor and the outer ground, which normally in an electrical world means, well, there's no electricity can flow across there at all. And normally that's true. However, when you're feeding electricity at just the right frequency, the electrons in the atoms of this radiating element in the metal here, they take on the ability to now hop to a higher orbit, electron orbit, and with the flow of electrons coming across it, they don't like being at that higher orbit, and they drop down, and when they drop down to their normal level, they release a photon of light, which for us is going to be a photon of RF, electromagnetic radiation. And that's the kind of hard concept to get, is that how you can put voltage on here and there's almost no current, but if you look at, and the reason that there's no current is because the impedance is extremely high. There's, as far as the voltage is concerned, it's such a high resistance you can't give any current. However, when you hit that resonant spot, now all of a sudden your impedance goes down to, well, ideally is 50 ohms, and that's when now the voltage can actually deliver current. And you look at this and say, well, hey, well, deliver current how? Does it cut across the little insulator here? And the answer is no, we never have a current flow across the insulator. What it does is the electrons supposedly at each different spot have a different rate. So it's just imagine kind of like a water splashing up and going back down. But interestingly enough, as the electrons are going up and down on the radiating element here, they're also going in and out on the ground, coming in through the braid on your coax and back to the radio. So it's a kind of a push and pull up and down on the voltage and the electrons going back and forth. And when they hit that, like I said, when they hit it just right, they can make the electrons jump orbit and then emit radiation. So it's very complicated. There's a lot of math involved in it. It's extraordinarily complex for sure. But the important things for us is just to understand, what we're trying to do, how we're trying to take electricity coming in on a cable and how it transforms, and how what we're doing in the big picture is we're taking the the powerful magnets down at the PG&E power plant that are getting rotated, and we're taking part of that force that is occurring there, and we're pushing it down the line all the way until we get to right here, and we're using part of that force that's generated by waterfall or a dam or a gas powered steam plant, whatever the source of the power is. That energy is brought down here to put electricity up and down these rods and make the light shine. Because these, when they shine, what's coming out of the antenna is the exact same thing that comes out of a light bulb. It's just on here it's a lot lower frequency, and the rods and cones in our eyeballs cannot perceive the radiation coming off. But it's coming off of here just like it comes off a light bulb, and there's no difference with it. So, that being said, I have a very simplistic model here of what's going on. We have the input coming in from PG&E. We have a device here that's going to transform that electricity into another form of electricity, run that electricity up this wire, and this is going to simulate a radio vault and a radio. This is going to be the coax cable coming off the radio. It's going to go up the tower. It's going to go to the antenna, in this case light, and this is where the electricity is going to get transformed into electromagnetic radiation. And it's a matter of antenna design as far as the VHF antennas, the regular 2-ways, as to what kind of light pattern that they produce. Whether in this case it's similar to a Yagi antenna, if you will, where it's directional, or maybe it's just an omnidirectional with no control at all, and it's just going out in all directions. Or in the VHF world, it could be a gain antenna, which if you take several of the elements and stack them on top of each other, provide the same amount of power and split it amongst the different elements. If you look down from space, it would appear that the antenna got less bright because more of the radiated power went out the side lobes than it went out the top. And that's how they construct gain antennas on the VHF. Yeah, like I said, all depends on the different mechanical structure, whether you have reflectors and directors, or what exactly you want to try and do with the antenna. But the concept is the same. You have the radio producing electricity. Electricity goes up the two wires, the coaxial wire, up to the antenna where it's transformed into electromagnetic radiation. So, that's the typical world of VHF. Now, I have here an example. This is a VHF quarter wave antenna. Here is an example of a UHF quarter wave antenna. And believe it or not, this is a 6 gigahertz antenna. So you can see why maybe if you had an antenna like this, it wouldn't be the best idea to put it up on the tower, or maybe there's a lot of loss that could happen. But the bottom line is that on all of our microwave radios, the antenna, if you will, because people always ask, well, hey, why don't you just hook up a watt meter to your microwave radio to see if you got any antenna problems? Well, here I'm using a SWR bridge to show you what the sweep looks like. This is starting at 6 and stopping at 7 gigahertz. You can see it's a nice antenna there. And it's got a really cool interior here where it's got some tuned circuits. It's kind of really crazy how they design these things, but that's how they basically tune the antennas, with those little walls and little things sticking out. This little teeny white thing right here is your sample port antenna. Believe it or not, yeah, that little 1/8 of an inch thing is an antenna. And so in the microwave world, our antenna coax cables end up only being a few inches or a foot long. They get transformed, the electricity gets transformed into light already at the radio, at what we call the top of the rack there, where the PA output goes into your first transmit filter here. So after it goes into this connection here, from here on it's light. It's no longer electricity on a coax cable. So what they do is they take the light that's inside the vault, they keep it in there, and they hook up a hollow reflective copper tube that's going to take that light and run it like a sealed mirror tube, like a fiber optic light. I'm sure you've seen those now. And they're going to take the light and they're going to run it all the way up to the tower, and through this hollow tube that's pressurized with air to keep water from getting into it and corrosion, and keeps it nice and pristine. They run the light through the tube up through what's called a feed horn assembly, and this light comes out, and what it does is it shines on a dish. Now this dish is concaved, and it can take the light beam and focus it into a tight, narrow spot. And it can take that and send it in a very narrow beam to where you want it. But the only thing the microwave dish is a reflector. It's just a big mirror with a feed horn thing that lets the light come out and shine in front of it, and then it kind of shines past it and around it as it goes out, just like in this situation here. So that's the difference between a microwave antenna and a VHF antenna. The thing on the dish is not really even an antenna. It's more of a reflector device. Much like a mirror is not a light bulb. It's just a mirror. But this is the real antenna. And it works the same in the reverse direction. So when the signal from the other end comes, it hits the mirror, it shines back into the feed horn, and then the light wave goes back down the tube, comes into the receive section, and hits an antenna just like this as well. And now that light coming in, as it crosses the section of antenna, it induces voltage and current back to what we know as regular electricity, flow of electrons. And that's what goes into your receiver, and then it's taken from there all the way through all of its processes. So when it comes to troubleshooting a microwave dish, it's not really very easy, because if you go to the bottom end where the radio is at and there's no signal coming in, well, it could be for a variety of things. Maybe your tube got crushed. Maybe the dish is off, and that's why you're not seeing the signals, because they got pushed off. Or maybe it's broken or damaged or whatever. But the troubleshooting process is not easy. You would literally need to have someone go up to the top, disconnect the dish from the waveguide, and then put a terminating load on it, and then you could sweep it and see how much signal loss you got through the waveguide, and say, no, our waveguide's good, it must be the dish, and vice versa. But when you're looking at the dish and you're saying, well, is it off, you either have to have another dish that you can look with to see if you can see a signal, or you have to try and use your own transmit hooked up to that dish, go to a ways down away and see if you can see a signal emanating from it. But it's not any part where you can hook up some kind of watt meter or something like that and say, well, hey, show me how much of this is getting through there. The only way that you know is by using your receiver at the other end. That's kind of like your only test equipment for getting the receive level coming back. And so, yeah, there you go. The microwave antennas are not easy to work on. And I hope this helps you guys trying to understand how antennas work. And I strongly encourage you to get completely comfortable with that idea of maximum power transfer, and that when you have a perfectly good antenna and a perfect radio, that both are going to dissipate the same amount of power. So if you're going into a perfect dummy load, you're going to have 100 watts of heat on the dummy load, and you're going to have 100 watts of heat on your PA assembly on your radio. That's why they get hot when you use them. So, all right, guys. Till next time.